Morning, good afternoon, or good evening, ladies and gentlemen. Welcome back to Unit 9B. Today we are talking about Lesson 9.5, which is the second lesson all about machines. Now, before we go any further, if you have forgotten anything about yesterday's lesson, or if you haven't looked at yesterday's lesson, please stop and go back and look at Machines Part 1, which was Lesson 9.4, before you do this lesson. If you don't do that, there will be certain things we talk about today that are just not going to make any sense at all. Okay? Everybody good? Everybody where they need to be? Fantastic. Let's keep going. So we're going to start off today by talking about mechanical advantage, and we will abbreviate mechanical advantage as MA because that's just a really long word to keep writing over and over and over again. Mechanical advantage is a number, and it tells you how many times a machine multiplies the effort force. In other words, folks, it tells you how much easier a machine makes work. The bigger the mechanical advantage, the easier it will be to do a certain job using that particular machine. So if you're all about doing things the easy way, then you want to use a machine that has the largest possible mechanical advantage. Now we can divide mechanical advantage into two categories, big and small. Remember, mechanical advantage is always a number. It's just a number. It doesn't have any units. But we can divide it into mechanical advantages that are bigger than 1 or greater than 1. And we can divide it into mechanical advantages that are smaller than 1. If the mechanical advantage of a machine is bigger than 1, it makes the work easier to do, but slower. It takes longer. So that's the trade-off. You can use less force, but it will take more time. If the mechanical advantage of a machine is less than 1, it makes the work harder. It requires more force to do the work, but it gets the work done faster. So it just depends on what type of job you're trying to do, which type of machine you would choose. So let's take a look at an example of a machine that has a big mechanical advantage, and that would be a crowbar. Imagine using a crowbar to pry open a crate. It makes it much easier to lift open the planks. However, you have to move the handle of the crowbar through a much longer distance compared to the distance that the plank moves as you pry it loose. So, you use less force to do the job, but you have to apply the force over a longer distance. This is an example of a machine that has a mechanical advantage greater than 1. A golf club is an example of a machine that has a mechanical advantage of less than 1. Wait, a golf club is a machine? Yes, absolutely. Okay, a golf club is used to transfer force and energy from one object to another, from a person to a golf ball. All right, you move the handle through a relatively short distance. Meanwhile, the club moves through a very long distance. You have to apply a lot of force to the handle over a short distance. The trade-off is that the head of the club moves very, very, very fast, so that when it hits the ball, it'll really send that ball flying 300 yards, no problem. Okay? When we calculate the mechanical advantage of a machine, we can either talk about the ideal mechanical advantage or the actual mechanical advantage. If we say something is ideal, that means it's perfect. It's, exactly the maximum amount that it could be. And the ideal mechanical advantage is equal to the effort distance divided by the resistance distance. So this is where we learned about this yesterday in lesson 9.4. And if you do not recognize these terms, then you should definitely go back to 9.4, rewatch that video, and then come join us here again. The actual mechanical advantage is equal to the resistance force divided by the effort force. And again, these terms come from lesson 9.4. The actual mechanical advantage is always going to be less than the ideal mechanical advantage. The ideal mechanical advantage is what you would get in a perfect world. The actual mechanical advantage is what you really get. When you take into account the fact that all real machines have to deal with friction, and friction causes the mechanical advantage of a machine to decrease. So the AMA is always going to be less than the IMA. If you're ever doing some calculations, and you come up with the AMA bigger than the IMA, then that means you should go back and check your math, folks, because there might have been a mistake somewhere. AMA should always be less than IMA, never greater. So if you remember yesterday, we were talking about this situation where our friend Frank here is pushing a box up a ramp. He is using a force, an effort force of 200 newtons to move the box over an effort distance of 5 meters. The resistance distance is 2 meters, and the resistance force, which is equal to the weight of the box, is 400 newtons. So we want to calculate the IMA and the AMA of this ramp. We'll start with the IMA. Remember, the IMA is equal to the effort distance divided by the resistance distance. The effort distance, or the distance that Frank has to push the box, is 5 meters. The resistance distance, the distance that the ramp physically lifts the box, is only 2 meters. So the ideal mechanical advantage is 5 meters divided by 2 meters, which is 2.5. What that means is if there was no friction at all, then this ramp would make it 2.5 times easier to push the box up the ramp than it is to just lift the box straight up. Now let's work out the AMA, the actual mechanical advantage. To do that, we take the resistance force divided by the effort force. The resistance force is almost always equal to the weight of the thing that's being moved, and the effort force is how much force Frank has to use to push the box. So that's 400 newtons divided by 200 newtons. And when we do that math, we come up with an actual mechanical advantage of 2. 2 is less than 2.5, which is exactly what we would expect. We expect that the actual mechanical advantage is going to be less than the ideal mechanical advantage. And the reason is because there's friction between the box and the ramp that steals away some of the mechanical advantage. So it is still easier to push the box up the ramp than it is to lift it straight up, but it's only 2 times easier instead of 2.5 times easier. Next, let's talk about work input versus work output. Work input is how much work you, or Frank, or whoever does pushing a box up a ramp or using a lever to lift the load or whatever it is you're doing with the machine. And that's equal to your effort force times your effort distance. Remember, work is always force times distance. So for work input, we're using effort force and effort distance because that's what you're putting into the machine. Work output is equal to resistance force times resistance distance because that is the work that the machine is putting out. And as always, work is going to be measured in joules. So let's change back to our situation with Frank. He's still pushing that box up the ramp. Will he ever reach the top? Let's calculate his work input and work output. His work input is equal to the effort force times the effort distance. Frank is pushing with a force of 200 newtons over a distance of 5 meters. 200 times 5 is 1,000. So Frank will do 1,000 joules of work pushing the box up the ramp. Now the work output is equal to the resistance force times the resistance distance, which is 400 newtons times 2 meters, or 800 joules. Again, we see that the work output is less than the work input. What happened to those missing 200 joules? They turned into heat because of friction. As the box slid up the ramp, the bottom of the box and the top of the ramp got hotter because of the box scraping against the ramp, and that's where the missing 200 joules went. The work output should always be less than the work input in a real machine because of things like friction stealing energy and mechanical advantage away. And so the last thing we want to talk about is efficiency. Efficiency is a measurement of how well a machine is working. To calculate the efficiency, you take the work output divided by the work input and multiply that number by 100 to turn it into a percentage. You'll know you're setting this up correctly if the work output is less than the work input. You should never have the bigger number on top when you're calculating efficiency. The smaller number should always be on the top because the efficiency of a real machine should always be less than 100%. So back to our friend Frank pushing the box up the ramp. To calculate the efficiency, we take the work output. Well, we just figured out that the work output was 800 joules. It was 400 newtons times 2 meters. Divided by the work input, which is 1,000 joules, or 5 meters times 200 newtons. 800 divided by 1000 is 0.8, and then we multiply that by 100, which just moves the decimal 2 places to the right and gives us our final answer of 80%. This machine is 80% efficient, which means that for every 100 joules of work that Frank does pushing the box, only 80 of those joules actually go into lifting the box. The other 20 out of every 100 joules get transformed into heat, as we talked about previously. So we're going to test our knowledge of all these equations that we have learned in a new situation. Let's read it together. What are the ideal mechanical advantage, actual mechanical advantage, work input, work output, and efficiency of this lever? So here we have a guy pushing a lever. He is going to push the lever a distance of 1 meter, exerting a force of 60 newtons. And on the other end of the lever will rise only half a meter and will lift a weight of 100 newtons. Okay, let's start with the IMA. The ideal mechanical advantage, remember, is equal to the effort distance divided by the resistance distance. The effort distance is how far a person pushes on the lever. That's going to be 1 meter. The resistance distance is how far the opposite end of the lever moves, and that's 1/2 a meter, or 0.5 meters. So grab your trusty calculator, or maybe you can do this in your head. 1 divided by 0.5 is going to give us an ideal mechanical advantage of 2. In other words, if it weren't for friction or any other forces, this lever would make it twice as easy to lift that load. Now let's calculate the actual mechanical advantage, see how much easier it actually is. To find the actual mechanical advantage, we take the resistance force divided by the effort force. The resistance force is the weight of the box, so it's 100 newtons. The effort force is how much force our friend has to use to push his end of the lever, and that's 60 newtons. So we have 100 divided by 60, which is going to wind up being 1.6 repeating. So I'm just going to round that off to 1.67. Now's the time to stop and make a reality check. The AMA should be less than the IMA, and we see that that is the case, and that's exactly what we would expect. Because this lever is not a perfect machine, because it has friction and the lever will bend a little bit, that will absorb some of the mechanical advantage. The actual mechanical advantage is going to be less than the ideal mechanical advantage. Next, let's figure out the work input. The work input is equal to the effort force multiplied by the effort distance. The effort force is 60 newtons, because that's the amount of force that this person is using to push on the lever. The effort distance is 1 meter, because that's the distance that he pushes the lever. 60 times 1 is 60, and a newton times a meter is a joule, which is the unit for work. Now let's figure out the work output. The work output is equal to the resistance force multiplied by the resistance distance. The resistance force is the weight of the box, so that's 100 newtons. And the resistance distance is the distance moved by the box, which is 0.5 meters. 100 times 0.5 is 50, and newtons times meters is joules. So again, we stop and check to make sure everything's making sense. The work output should be less than the work input, and it is. 10 joules of work have gone missing, probably because as the lever moves, it experiences friction as this part spins. And so finally, we calculate the efficiency of this lever. The efficiency is going to be equal to the work output divided by the work input, and then we will multiply that result by 100. The work output is 50 joules, so put that number on top. And then the work input is 60 joules, so that goes on the bottom. Remember, the number on top should be less than the number on the bottom, because we want to get an efficiency that's less than 100% to be realistic. 50 divided by 60 is 0.83, and it's going to be repeating. It's going to keep on going forever and ever. And then we're going to multiply that by 100, so we will move the decimal 2 places to the right, which means that the efficiency is roughly 83%. So folks, that is going to bring us to the end of lesson 9.5. Please head on over to Google Classroom where I have an assignment for you to do, and join me tomorrow when we will be talking about lesson 9.6, which is all about simple machines. There are 6 types of simple machines that we'll be discussing tomorrow. As always, take care of yourself. I hope you're doing well. Keep on washing those hands, and we will see you tomorrow. Have a great day. Bye.